afternoon. Good afternoon, everybody. I'm a PhD student from Lisbon, and I'm not really used to do this, so I'm nervous, but I'm always so very pleased to do this presentation. So, what is polyclonal selection? It was developed in Portugal as part of a methodology to preserve and improve grapevine varieties, and is performed over a large field trial with a representative sample of the intravariable variability of the variety, and based on quantitative genetics and linear mixed models theory. The objective of the polyclonal selection is to select a group of different genotypes that, taken together, meet the selection criteria to the desirable traits. So the predicted genetic gain of this group are calculated as the average of the predictors of genotypic effects of the genotypes that compose that group. Our problem was to find a way to maximize the genetic gains of the group. Selection indices were not ideal because they focused on the individual gains and rather than the group gains. So, and we want to achieve the gains of the group as a team. Selection indices focusing in the individual gains can lead to some unwanted losses when we select the group. So our approach was to look at this as an optimization problem in which we want to maximize the predicted genetic gain of the group while using the constraints to avoid the losses. This is our problem, and X is our decision variable. It equals 1 if the genotype is selected, or 0 if it is not. The Y is the predictor of genotypic effects divided by the overall mean of the trait. The S is the number of clones to be selected, the clones, because we are talking about grapevine when this was developed. And the other constraints are for the traits. The LK is defined like this to maintain the linearity, and the RK, it's the desired minimum gain for the trait as a percentage of the mean. On the other side, if we use only one trait in the objective function and no constraints, we can assess the maximum possible gain. That is, the gain possible to achieve or obtained when we select the top S genotypes in the group for that trait. Now, keeping only one trait in the objective function, but adding constraints to the other traits to be greater or equal than 0, we can assess what we called the maximum admissible gain. That is the gain, the maximum gain possible to achieve with the selection to a trait without inducing losses in the other traits. So to make it easier to apply this method, we developed the package maximisation that are now available on CRUN and has three main functions. The polyclonal, which implements the method in its full formulation. The Rmax-P, that computes the maximum possible gain, and Rmax-A to the maximum admissible gain. The package also includes data set with envelopes of genotypic effects obtained from real data from a field trial with 150 genotypes of the Portuguese grapevine variety Gouveia. The trial follows a resolvable row column design. Several traits were evaluated, and the selection criteria in this work was to increase yield, potential alcohol, and total acidity while decreasing the berry weight and the pH. So this is an example of the application of the polyclonal function. We have the argument traits to indicate the traits we want to optimize. The CL min and CL max allow us to define a range of group sizes that we want to obtain. In this example, we ask for groups from 7 to 12 genotypes. The DMG argument is used to define the constraints. It's given as a data frame with 3 columns, the first for the traits, the second for the relation, the sign of the constraint, and the third for the minimum desired gains. Note that here the minimum desired gain are indicated as a percentage of the mean. The mean vac is to indicate the means of the several traits, and the criteria we ask for 1 if we want to increase and -1 if we want to decrease. Sorry. So this is the output of the polyclonal function. As an example, it has 2 objects. In fact, all the other functions also have these 2 objects. The object gain gives us the predicted genetic gains as a percentage of the overall means for the several traits and per group size. Looking here, we can see that not the total of group sizes asked were possible to achieve. So we have gains for the group of 7, 8, and 10 genotypes. Another important note is that in this output, all the positive values are values according to the selection criteria. Thus, the values of 1 and around 2% for pH and berry weight are, in fact, decreases obtained by this group because that was the initial criteria. Thus, the object selected lists the several genotypes that compose each group. And note that with this method, contrary to what happens with the selection indices, the genotypes belonging to the group of 7 are not necessarily included in the group of 8 or greater groups. So this is the summary of polyclonal function. allow us to know immediately that only 3 groups were obtained and the sizes of those groups, and the initial conditions and the maximum gain possible to achieve in each trait and the dimension of the group in which that gain was achieved. So we can see, for example, that for yield, we have a gain of around 24% in the group of 7 genotypes, while for total acidity, the gain, the maximum achieved was 4 in the group of 8 genotypes. So, to conclude, this method really enables the selection of genotype groups for several traits simultaneously in a multi-trait scenario, and controlling the gains, not only avoiding the losses, but really controlling the gains desired for each trait. Although it was originally developed for grapevine, it can be used to other species whenever the goal is to select genotypes, groups. And the package improves the usability because it's easier to indicate a range of groups or to indicate the gains, as a percentage of the mean instead to do all the conversions. So I'd like to thank my supervisors, my colleagues, and everybody who are in some way related to these trials and to the obtain of this data. And of course, to thank you all for the attention.
Thank you so much.